So how are we, guys? So I'm going to talk a little bit about some multiphysics and some optimization. Brody's already touched on a bit of the multiphysics and optimization, so I'll run through this quickly, and I've got a bit of a presentation about how I used it in the FSAE, so part of the RMIT team from the previous year. So I talked about this on the first day, but when it comes to students, where we've come to understand and really analyze single physics problems. However, as we develop as an engineer, we're going to need to get to the point where we interact with different physics. So a FSAE and UAV experience is, again, looking at that wing. So we had something we can do a fluid analysis. We can get the forces out of that, understand what the deflection is, and then go through the parameter set and actually improve, looking at how the plies drop off, what orientation, and anything else we want to look at. So going into optimization, though, we've got a couple of different tools that we can use for it. So we've got topology optimization for structural. We've got something called the ADJOINT solver for fluids. We've also got embedded this thing called design of experiments, what-if scenarios we can use as well, and we can also pull out some response surfaces and some goal-driven optimization. So we'll first look at the topology optimization. So these are all examples from the tutorials that we've created. So what we can see here is just as a bell crank. So what we've done, instead of doing a full 3D analysis, which can take quite a long time, we've simplified this problem to 2D. We can first run through and do some sort of simulation with whatever loading condition that we need. And we can see here that we've got quite a bit of material that's underutilized. And you can see that through the blue regions, which is pretty much no stress going through them. So what we can do using this stress analysis, we can use it to reduce the amount of weight. So I know some of you guys have already done it, but the optimization algorithm first determines the material that can be removed. And it determines it by the input parameters. So looking at the stress, displacement, and any other input variables. So the program removes elements by effectively giving it a zero stiffness value and then rerunning the simulation. So we can do a couple of iterations to figure out exactly what we need and what the structure should look like. So it goes to that iteration loop, and then we can go back, look at the actual structure. We can recreate it in SpaceClaim or any of the material, the CAD softwares that we have, and then reanalyze. So in this case, we just did a static structural analysis, but we can then go back, look at this new shape, and do some sort of fatigue testing, or we can do a vibrational analysis. So what also we have is called the ADJOINT solver. So it's a part of a process for computational fluid dynamics. So the solver is based around moving the deformable mesh. To do this, it implements a Brainstorm polynomial-based morphing scheme. So what this does is that it performs a free, smooth, free-form mesh deformation around a matrix, and it's able to do that with quite large deformations without twisting the grid or creating an unstable mesh. So it can be used, and it's directly applied to the actual geometry. However, it keeps the original data. So the benefit of this is that instead of going through and making a design iteration, changing the geometry, doing it again and again and again, the software will actually to move the geometry around. So we've got an example here of a wing profile. So we can use this software to increase the CL. So you can see here that we've got this nice structured mesh. We've given this matrix, we've given a couple of points, and we can say, improve the CL. So we'll go through, it'll make a couple of deformations to the structure in order to get the CL that's improved. We can then take that structure, redo the analysis on the final shape. So another thing that we can do is called what-if experiments. So what we want to do is we can observe any big changes, right? For instance, in our case, how many elements should I use to get downforce of a certain amount on the front wing? Should I go for a 1, 2, or triple element? So first thing is understanding the first principles. So understand what static pressure is, really understand the basics. The next case is a bit of parametric CAD. So ANSYS has the ability to be bidirectional. So you can make, say, a change in NX, Creo, or SolidWorks. And you can actually update that. It updates straight away into SolidWorks. Or you can have it run through Design Modeler. We can then run the simulation and review what's actually happening, what are my results, what do I expect, make a hypothesis. So, all right, let's say I've got these wingtip vortices. Well, I've done some reading and I know I've got end plates that I can use. So I think if I whack these in, this is what's going to happen. Rerun the simulation and then have a look and rinse and repeat. So make adjustments to your CAD, update through answers. So this is a very what if, making major changes. What we can do is then we can say, take those wing profiles and then do something called the design of experiments that was previously touched on. So what we can do is say, all right, look at my wing angle, and I want to say, I want to change my wing angle, and I want to sweep it from 0 to 20 degrees. And I want to figure out, say, where do I separate? So where's my max downforce figure? So I can run through that. So it's got DOE tools integrated into it. And it depends on any inputs that you put in, and you can actually get some outputs from that. So you can have an output of a CL or CD. So what happens is that you make these changes. The software runs through, make the geometry changes in the background, runs through the simulation, outputs this file, and it goes to the next step. So you can have it all set up, and you can have it such that it's essentially scripted. Response surfaces is also something that we can use, and it's a way of representing something in 3D or 2D space. It enables you to visualize what's happening. So for each response, we can actually see a combination of inputs and outputs to understand about the actual problem. We can then use it to also understand the sensitivity between a couple of different issues and how certain parameters can affect other ones. So using this data, you can then do something called a direct response. So we can say, all right, if I want to say maximize my efficiency, I can put that as a parameter. It'll run through the DOE, have a bunch of different outputs, and it'll actually give me, based on a couple of stars, which ones are actually the correct parameters that I should be looking at. So there's a lot more functionality involved within ANSYS. So do come talk to us if you want to talk about that, or even things like scripting. That's not for the optimization side of things. I'll go into the team presentation. Scott, do we have anyone else that? No. Do we have any, did we have any questions about, we went over just a little bit because we've got quite a bit of tutorials. Do we have any questions about optimization or about multiphysics or anything like that? No. That's cool. All right, so this is a little bit about how I used DOE, so design of experiments, and also a bit of what-if study to improve the front wing of the RMIT car last year. So this is a part of one of my projects. So the idea was that, it's a very simple current design. We need to make a little bit more front downforce, and the objective was to evaluate the ground clearance and flap angle that produces the most amount of downforce. So the methodology. So I first did a 2D CFD simulation. The reason for that, there were quick run times. It enables you to check out 2D flow structures, and we can do quite a bit of experiments. So we can sweep through a lot of flap angles with a lot of different ground clearances as well. Looking at that data, we can then hone on in areas that create quite a bit of downforce and do a full 3D simulation. So the issue with this, though, depending on your computer, it can take quite a bit of time. So we don't want to be doing too many, but you can quite clearly see the vortex structures and the complexity in 3D flow. And then using that design, we can then go through and do some what-if, some design iterations. What could have been done afterwards is looking at things like a joint solver, which was touched on, that some of the F1 teams use, or also using some of the other softwares involved. So the first thing is the geometry. So we've got this 2D geometry that was created. It's just looking at the two main elements. There's nothing fancy about that. So this is something everyone can do. It is a 2D wing in CFX or Fluent. And we've got a sample of the 3D geometry there. So it's again, I don't need to look at the whole wing profile. I was really interested in just these two elements because I think these are the ones that will make the most amount of difference. So the first thing again was doing that 2D design of experiments. So they're the data points at the top here. So looking at the graph, we've got different flaps at different ground clearances. So we've got ground clearances on the X, we've got different flap angles. And you can see that the red stars indicate where you've got roughly the most amount of downforce. So focusing on these areas, we then started a 3D analysis, which are the ones at the bottom. And using that, we were able to determine roughly at what point do we make the most amount of downforce. So you can see that there's a large difference in the CL seen on a 2D wing compared to a 3D wing. So why is that? So if you look at the pressure distribution, so the one on the left-hand side is the 2D, and over here is the 3D profile. So we've got some nice clean flow, it's all going in one direction, and we've got this nice pressure distribution. However, on the 3D side, you can see that due to the flow fields, due to things like vortices being created, due to high pressure and low pressure regions, we don't have this nice clean change in pressure that we'd expect. So one of the first things that we did is that, I looked at the actual initial wing design. So it had a fixed end plate and a fixed angle, and you can see the flow structure. So the first iteration was a matter of increasing the end plate and also adding some sort of foot plate. So you can see that here. And you can see a comparison between the first and second iteration, where you've got a larger lower pressure region around the middle, showing that we've got a little bit more, we've got more downforce that's created. The next thing was I did a little bit of literature, and I saw there were a couple of teams that were running, cut end plates, so that was to improve efficiency in yaw, but they also had some flaps around the top. So you can see, looking at that, this is a vortex core, so you can see the vortex that comes off and gets pushed away from the wing. However, that didn't see it too much, didn't see quite a big, increase in gains. So the next thing was looking at something like strakes. So you can see here, looking at the pressure distribution, the strakes really control the vortices that come off the end plate, and you've got, again, a larger lower pressure distribution against the main element. So overall, there's around improvement around 15 to 20% within the actual design. So this was just focused on the front wing. So you can see here where we use a 2D kind of design of experiments due to its quick runtime to figure out roughly where should I start. We then looked at the 3D cases. We did some what-if studies. So what if I had a bigger end plate? What if I had a flat? What if I had some strakes? And what we can do, we can also then kind of take that a step forward. We can do some joint, so we can use the software to change the actual shape.